In the beginning there was light, not the light of metaphor or myth, but the light that crosses the void between stars, that carries the warmth of distant suns, that bends through the fabric of space itself. For as long as human beings have looked upward into the darkness, we have been messengers received by starlight, photons that began their journey before our ancestors walked upright, before continents found their present shapes, before the very ground beneath our feet had cooled from its molten birth. We are creatures bound by light, both illuminated and confined by its absolute speed, and for generations we have accepted this boundary as the final word written into the structure of reality itself. But science, unlike myth, does not rest. It questions, it probes. It imagines the impossible, and then asks whether the impossible might, under certain conditions, become merely improbable. And in recent years, a small community of physicists, mathematicians, and cosmologists have returned to an old dream with new tools, proposing mechanisms that do not break the laws of physics, but instead navigate around them with such elegance that the universe itself might permit what we once thought forever forbidden. Before we venture further into this extraordinary frontier, take a moment to settle in, to expand this window to full screen, and if this journey resonates with you, consider subscribing so we might continue exploring these profound questions together. Now, let us begin. The speed of light is not simply fast. It is not merely a number to be measured and recorded. It is woven into the very grammar of the cosmos, a fundamental constant that dictates how cause relates to effect, how energy transforms into mass, how time itself flows differently for observers in relative motion. When Albert Einstein published his special theory of relativity in 1905, he did not discover the speed of light, he discovered what the speed of light means. He revealed that light does not travel through space at a particular speed because the universe happens to be constructed that way, but rather that the speed of light represents something deeper, an invariant feature of spacetime itself, the maximum rate at which information, causation, or influence can propagate from one point to another. This is not a technological limitation, not an engineering problem waiting for a clever solution. It is, according to the mathematics that have been tested and confirmed across more than a century of experimentation, a structural feature of reality. Consider what this means. If you were to accelerate a spacecraft, applying continuous thrust, burning fuel, converting mass to kinetic energy, you would begin to approach the speed of light. But as you accelerated, something strange would happen. From the perspective of an observer at rest, your mass would appear to increase. Not because new matter is being added, but because the energy of motion itself contributes to the relativistic mass of the moving object. As you approach closer and closer to the speed of light, this effective mass grows without limit, and so too does the energy required to accelerate further. To reach the speed of light would require infinite energy. To exceed it would require something beyond infinite energy, a concept that dissolves into mathematical nonsense. This is the barrier, the cosmic speed limit, and it is enforced not by any law or decree, but by the shape of spacetime itself. Yet we know, with certainty, that the universe is vast beyond human comprehension. The observable universe extends roughly 93 billion light-years in diameter, a distance so immense that light itself, traveling at its maximum speed without pause or deviation, would require 93 billion years to cross it if such a crossing were possible. But the universe is also expanding, and distant galaxies recede from us at velocities that, when accounting for the expansion of space itself, exceed the speed of light relative to our position. These galaxies are not moving through space faster than light, they are being carried by the expansion of space, and this distinction is crucial. Space itself is not bound by the speed limit that governs objects moving through space. This observation, confirmed through decades of astronomical measurements, hints at a possibility. If space can expand faster than light, if the metric of spacetime itself can change in ways that carry distant regions apart at superluminal velocities, then perhaps the fabric of spacetime can be manipulated in other ways that might allow an object, a spacecraft, a human being, to traverse vast distances without ever violating the local speed limit. This is not science fiction, though science fiction has long dreamed of it. This is a question being explored in peer-reviewed journals, in university physics departments, in the quiet offices of theorists who spend their days manipulating tensors and field equations, seeking solutions to Einstein's equations that permit what we might call effective faster-than-light travel without breaking the fundamental rule. The proposal that has recently gained attention, the new way some scientists are suggesting we might one day travel faster than light itself, rests on a concept that sounds impossibly abstract at first hearing but becomes, upon reflection, almost intuitive. It involves not moving through space at high speed, but rather manipulating the space around a vessel so that the vessel itself remains stationary in its local frame while space contracts ahead of it and expands behind it, effectively carrying the vessel across vast distances in arbitrarily short times. This concept has a name. It is called a warp drive, and while the term may evoke images of science fiction, the underlying physics is rooted in solutions to the Einstein field equations. The set of 10 interrelated differential equations that describe how matter and energy curve spacetime and how that curvature in turn dictates the motion of matter and energy. In 1994, a physicist named Miguel Alcubierre published a paper describing a particular solution to these equations, a configuration of spacetime in which a bubble is formed around a spacecraft. Within this bubble, space is flat, and the spacecraft experiences no acceleration, no time dilation, no violation of local physics. But outside the bubble, space is arranged in a very specific way. Ahead of the bubble, space contracts, bringing distant points closer. Behind the bubble, space expands, pushing previously close points farther apart. The net effect is that the bubble, and the spacecraft within it, moves relative to distant observers at speeds that can, in principle, exceed the speed of light, while the spacecraft itself never moves faster than light relative to the space immediately surrounding it. The Alcubierre drive, as this solution came to be known, was initially regarded as a fascinating curiosity, a mathematically valid but physically implausible toy model. The reasons for skepticism were numerous and formidable. First, the energy requirements appeared to be astronomical, not merely in the colloquial sense but in the literal sense. Early estimates suggested that creating such a warp bubble would require a mass energy equivalent to the entire mass of Jupiter, concentrated and manipulated in ways that no known technology could achieve. Second, the type of energy required was not ordinary matter or even ordinary energy. The equations demanded negative energy, or more precisely, exotic matter with negative energy density, a substance that, if it exists at all, has never been observed in nature and may be forbidden by the laws of quantum field theory. Third, there were concerns about causality, about whether such a drive could be used to travel backward in time, creating paradoxes that would undermine the logical consistency of the universe. And fourth, there were questions about stability, control, and whether a warp bubble, once created, could be maintained, steered, or safely collapsed without catastrophic consequences. For years, these objections kept the Alcubierre drive in the realm of theoretical curiosities. It was discussed in academic papers, analyzed in doctoral theses, occasionally mentioned in popular science articles, but it was not taken seriously as a blueprint for actual propulsion. Yet science does not discard ideas simply because they are difficult. Science refines ideas, tests them, modifies them, and sometimes discovers that what appeared impossible under one set of assumptions becomes merely challenging under another. Over the past decade, several physicists have revisited the warp drive concept, asking whether the objections that initially seemed insurmountable might be mitigated or even eliminated through clever modifications to the original proposal. One of the most significant developments came from a physicist named Harold White, who worked at NASA's Johnson Space Center. White and his colleagues examined the Alcubierre metric more carefully, exploring whether changes to the geometry of the warp bubble might reduce the energy requirements. They discovered that by altering the thickness of the bubble wall by adjusting the shape from a simple sphere to a more toroidal or donut-like configuration, the energy requirements could be reduced dramatically, from Jupiter mass scales down to something closer to the mass of a spacecraft like Voyager. This was still an enormous amount of energy, far beyond what current technology can generate or manipulate, but it represented a reduction of many orders of magnitude, a shift from obviously impossible to merely extraordinarily difficult. More recently, other researchers have proposed further refinements. Eric Lentz, a physicist at the University of Göttingen, published work suggesting that it might be possible to construct a warp drive using only positive energy, eliminating the need for exotic matter altogether. Lentz's approach involved arranging ordinary matter and energy in highly specific configurations, creating soliton-like structures in spacetime that could propagate faster than light. These solitons, stable wave packets that maintain their shape as they travel, would require immense energy densities comparable to the output of stars, but they would not require the theoretically problematic negative energy that plagued earlier models. This proposal has not been without criticism, and many physicists remain skeptical about whether such configurations could be achieved in practice, but the work represents a shift in the conversation. The question is no longer whether faster-than-light travel is absolutely forbidden, but rather whether it is achievable given sufficient technological advancement and energy resources. Another line of inquiry has focused on understanding the fundamental nature of spacetime itself at scales far smaller than those accessible to current experiments. Quantum field theory, the framework that describes the behavior of particles and forces at the smallest scales, predicts that empty space is not truly empty. The vacuum is filled with fluctuations, virtual particles that pop into and out of existence on timescales so brief that they cannot be directly observed, but whose effects can be measured through phenomena like the Casimir effect, a tiny attractive force between uncharged metallic plates placed very close together in a vacuum. These vacuum fluctuations represent a kind of energy, and under certain conditions, this energy can be negative relative to the surrounding vacuum. Some physicists have speculated that if we could harness or manipulate these vacuum fluctuations, we might be able to generate the exotic matter required for an Alcubierre-style warp drive. The Casimir effect, discovered experimentally in 1948, demonstrates that quantum fields can produce measurable forces even in regions considered empty. Between two closely spaced plates, certain wavelength of virtual particles are excluded, creating a region where the energy density is lower than in the surrounding vacuum. This lower energy density, this relative negative energy, exerts a pressure that pushes the plates together. The force is incredibly weak, measurable only when the plates are separated by distances on the order of nanometers, but it is real and reproducible. The question, then, is whether this principle could be scaled up, whether a sufficiently advanced technology could create and stabilize regions of negative energy density large enough and strong enough to warp spacetime on macroscopic scales. This is where the conversation becomes deeply speculative, yet grounded in physical principles that are, at least in theory, consistent with known laws. If spacetime can be treated as a dynamical field, subject to manipulation through the clever arrangement of energy and momentum, then the door remains open to engineering solutions that would have seemed like magic to previous generations. But we must be careful here. The fact that a solution exists mathematically does not guarantee that it can be realized physically. Mathematics is full of solutions that describe impossible or unphysical situations. A negative mass, for instance, appears in certain equations, but has never been observed, and may violate deeper principles of stability and causality. Similarly, a warp drive solution may exist as a valid solution to the Einstein field equations without being something that the universe actually permits to be constructed. To understand why, we must delve deeper into the nature of energy conditions in general relativity. The Einstein field equations relate the curvature of space-time to the distribution of energy and momentum. But not all energy distributions are physically reasonable. Over the decades, physicists have formulated several energy conditions, constraints on the kinds of energy distributions that are considered physically plausible. The weak energy condition, for instance, requires that the energy density measured by any observer be non-negative. The null energy condition requires that the energy density measured along light-like trajectories be non-negative. These conditions are not fundamental laws in the way that the conservation of energy is a fundamental law, but they are motivated by physical intuition and by the desire to avoid solutions that lead to pathological behaviors such as time machines or violations of causality. The Alcubierre drive, in its original formulation, violates the weak energy condition. It requires regions of spacetime where the energy density is negative, and not just slightly negative, but substantially so. This requirement is the source of much of the skepticism surrounding warp drives. If the energy conditions are truly inviolable, if the universe does not permit sustained regions of negative energy density on macroscopic scales, then the Alcubierre drive cannot be built, no matter how advanced our technology becomes. But there is an important nuance here. Quantum field theory allows temporary violations of energy conditions on very small scales and for very short times, a consequence of the uncertainty principle. The Casimir effect, as mentioned, is one example. Hawking radiation, the theoretical emission of particles from black holes, is another. These phenomena suggest that the energy conditions are not absolute prohibitions, but rather guidelines that hold in classical physics and on macroscopic scales, but can be temporarily circumvented in quantum contexts. The challenge, then, is to determine whether these temporary small-scale violations can be amplified, stabilized, and harnessed to create the kind of sustained, macroscopic negative energy density required for a warp drive. Some physicists believe this is possible in principle, though extraordinarily difficult in practice. Others believe the deeper principles, perhaps related to quantum gravity or the holographic principle, will ultimately forbid such constructions. The debate is ongoing, and it hinges on questions that sit at the very frontier of theoretical physics, questions about the nature of space-time at the Planck scale, about the consistency of quantum mechanics with general relativity, about the ultimate structure of reality itself. Let us consider the problem from a different angle. Suppose, for the sake of argument, that we could generate the necessary exotic matter or arrange ordinary matter in the configuration suggested by researchers like Lentz. What would the experience of traveling in a warp bubble actually be like? From the perspective of an observer inside the bubble, the journey would be remarkably uneventful, because the spacecraft itself is not accelerating relative to its local spacetime. There would be no g-forces, no sensation of motion, no time dilation effects within the bubble. An astronaut could sit comfortably, experiencing normal time, normal gravity, normal physics. Looking out a window, if such a thing were possible, would be deeply strange. Light from the universe outside the bubble would be severely distorted, perhaps compressed into a narrow band or even rendered invisible depending on the speed and geometry of the warp. The view might resemble a tunnel of warped starlight, or perhaps nothing at all. A featureless void surrounding the bubble. Time would pass normally for the traveler, but vast distances would be covered. A journey to the nearest star, Proxima Centauri, roughly 4 light-years away, could in principle be completed in days or weeks rather than decades or centuries, depending on the effective speed of the warp bubble. From the perspective of an external observer, watching from Earth or from a distant space station, the warp bubble would appear to move faster than light, crossing light-years in days. But this is not a violation of relativity because the bubble is not moving through space in the conventional sense. Space itself is being manipulated. The region of space containing the spacecraft is being carried, much like a surfer on a wave, and the wave can move through the ocean faster than any individual water molecule. This analogy is imperfect, but it captures something essential. The spacecraft is not racing through space at superluminal speed. Rather, space is flowing around it in such a way that the spacecraft arrives at distant locations faster than light would traveling through unaltered space. This distinction is crucial for understanding why warp drives do not necessarily violate causality or create time travel paradoxes. In special relativity, faster-than-light travel implies the possibility of closed time-like curves, paths through space-time that loop back on themselves, allowing an object to arrive at an event before it departed, creating logical paradoxes. But special relativity assumes a flat, unchanging space-time. General relativity, which allows space-time to be curved and dynamical, opens the door to solutions where faster-than-light travel, in the sense of covering large spatial distances in short coordinate times, does not imply the ability to travel backward in time. Whether this is truly the case for warp drives is still debated. Some analyses suggest that warp drives could be arranged to create closed time-like curves, while others argue that additional constraints, perhaps related to quantum mechanics or the requirement of self-consistency, prevent such pathological solutions. The question of causality touches on deep philosophical issues about the nature of time and the structure of physical law. If the universe permits travel that, from some reference frames, appears to violate the usual ordering of cause and effect, then what does that tell us about the nature of time itself? Is time an absolute background against which events occur, or is it merely a parameter in a set of equations, something that can be twisted and folded like space? Modern physics leans toward the latter view, treating time as part of the spacetime continuum, inseparable from the three dimensions of space. In this framework, the past, present, and future all exist in some sense, laid out like points on a map, and the flow of time is an artifact of our particular perspective as beings moving through spacetime along a particular trajectory. If this view is correct, then the barriers we perceive against backward time travel may reflect not a fundamental prohibition, but rather the difficulty of finding trajectories through spacetime that loop back on themselves while remaining physically consistent. The proposal for a new way to travel faster than light, the refinement and rethinking of warp drive concepts, is not a claim that such travel is easy or imminent. It is a claim that such travel may not be fundamentally impossible. This is a significant distinction. For most of human history, we have divided the world into things we can do and things we cannot do. We can build bridges across rivers, but we cannot fly by flapping our arms. We can generate electricity, but we cannot turn lead into gold through chemical reactions. Some of these impossibilities are merely technological. We could not fly until we understood aerodynamics and developed engines. Others are absolute. Chemical reactions cannot transmute elements because they involve only the rearrangement of electrons, not the transformation of atomic nuclei. The question with faster-than-light travel is whether it belongs in the category of technological impossibilities or absolute impossibilities. The emerging consensus among a subset of physicists is that it may, surprisingly, fall into the former category. This shift in perspective has profound implications. If faster-than-light travel is merely extraordinarily difficult, rather than absolutely impossible, then it becomes a legitimate target for long-term research and development. It becomes something that might be achieved in centuries or millennia, given sufficient advancement in our understanding of physics and our ability to manipulate energy in space-time. This does not mean that we should expect warp drives in the near future, but it does mean that we should not dismiss the possibility out of hand. Science thrives on exploring the boundaries of the possible, on asking whether the limits we perceive are real or merely reflections of our current ignorance. Let us turn our attention now to the practical challenges that would need to be overcome to build any kind of faster-than-light propulsion system, whether based on the Alcubierre metric, the Lens-Soliton, or some future proposal yet to be formulated. The first and most obvious challenge is energy. Even the most optimistic estimates for the energy required to generate a warp bubble exceed the total energy output of human civilization by many orders of magnitude. We are talking about energy densities comparable to those found in the cores of stars, or in the vicinity of black holes, or in the first moments after the Big Bang. Harnessing such energy would require fundamentally new technologies, perhaps based on controlled fusion or antimatter annihilation, or the extraction of energy from quantum vacuum fluctuations or some mechanism we have not yet imagined. Controlled nuclear fusion, the process that powers the sun, has been pursued for decades as a potential energy source for human civilization. Fusion reactions release millions of times more energy per unit mass than chemical reactions, and they produce minimal radioactive waste compared to fission reactors. Yet, despite decades of research and billions of dollars in investment, we have not yet achieved sustained, net positive fusion energy on Earth. The technical challenges are immense, involving the containment of plasma at temperatures exceeding millions of degrees, the precise control of magnetic fields, and the management of neutron radiation. If we can overcome these challenges, fusion could provide the kind of energy density needed for advanced propulsion systems though even fusion energy would need to be collected, stored, and converted into the specific forms required for space-time manipulation. Antimatter represents an even more potent energy source. When a particle of matter meets its antimatter counterpart, they annihilate, converting their entire mass into energy according to Einstein's equation, E equals mc squared. The energy yield from matter-antimatter annihilation is roughly 100 times greater than that from fusion. The problem is that antimatter does not exist in significant quantities in nature, at least not in our region of the universe. It must be created artificially, a process that currently requires far more energy than the antimatter produces when it annihilates. Moreover, storing antimatter is extremely challenging because it annihilates upon contact with any ordinary matter. Specialized electromagnetic traps can confine small quantities of antimatter, but scaling this up to the amounts that would be needed for a warp drive, perhaps grams or kilograms, is a daunting engineering problem. Nevertheless, antimatter remains a theoretical possibility for powering advanced propulsion systems, and research continues on methods for more efficient production and storage. Beyond these known but difficult-to-harness energy sources, there are speculative ideas about extracting energy from the quantum vacuum itself. The vacuum fluctuations that give rise to the Casimir effect represent a sea of energy that, if it could be tapped, would provide an effectively limitless source of power. Some physicists have proposed devices called quantum vacuum plasma thrusters, which would use vacuum fluctuations to generate thrust. These ideas remain highly speculative and controversial, with many physicists doubting whether such devices could work in principle, but they illustrate the range of possibilities being considered for future propulsion technologies. The second major challenge after energy is the creation and control of the required space-time geometry. Even if we had access to unlimited energy, we would need to know how to arrange that energy to produce the desired curvature of space-time. This is not a simple matter of dumping energy into a region of space and hoping for the best. The distribution of energy and momentum must be precisely controlled in three-dimensional space, and in some formulations, must vary dynamically in time. This requires an understanding of general relativity and quantum field theory that goes far beyond our current capabilities. It requires the ability to compute, in real time, the Einstein field equations for complex, dynamically changing energy distributions. It requires the ability to generate and manipulate fields with precision on scales ranging from the microscopic to the macroscopic. It may require new mathematical techniques, new computational algorithms, perhaps even new physical principles that unify general relativity and quantum mechanics in ways we do not yet understand. The third challenge is stability and control. Suppose we succeed in creating a warp bubble. How do we ensure that it remains stable? How do we steer it? How do we stop it? The mathematical solutions that describe warp drives typically assume that the energy distribution is maintained indefinitely, but in reality any physical system is subject to perturbations, fluctuations, and decay. A warp bubble might collapse spontaneously, releasing enormous amounts of energy in uncontrolled ways. Or it might become unstable, growing uncontrollably or fragmenting into smaller bubbles. Some analyses suggest that warp bubbles might be inherently unstable, unable to exist for more than brief moments before dissipating. Others suggest that stability might be achievable with the right configuration and feedback mechanisms, much like a plasma in a fusion reactor can be stabilized by carefully tuned magnetic fields. Steering a warp bubble presents its own difficulties. In the Alcubierre model, the spacecraft inside the bubble is causally disconnected from the bubble's edge. The spacecraft cannot send signals to the leading edge of the bubble to adjust its trajectory because those signals would travel at the speed of light, which is slower than the warp bubble itself. This creates a kind of control paradox. How can the occupants of the spacecraft direct their journey if they cannot interact with the mechanism that is carrying them? Proposed solutions involve pre-programming the trajectory before entering the bubble, or using external guidance systems, or finding ways to modify the warp bubble from within using exotic physics that we do not yet understand. None of these solutions is satisfactory, and they all highlight the enormous gulf between a theoretical solution to an equation and a practical controllable technology. The fourth challenge is safety, both for the travelers and for the universe at large. A warp drive, if it could be built, would concentrate enormous energies in a small region of space. Mistakes, malfunctions, or instabilities could result in catastrophic releases of energy, potentially destroying the spacecraft and anything nearby. There are also concerns about the effects on spacetime itself. Some models suggest that warp bubbles might leave behind distortions or scars in spacetime, regions where the fabric of space has been permanently altered. If warp travel became common, these scars could accumulate, potentially affecting the large-scale structure of the universe or creating hazards for future travelers. There are also speculative concerns about the emission of radiation. As a warp bubble moves through space, it might accumulate particles and radiation at its leading edge, only to release them in a burst when the bubble collapses. This burst could be intense enough to sterilize entire planets or disrupt solar systems. These scenarios are highly speculative, based on incomplete models and uncertain physics, but they illustrate the need for caution and careful analysis before attempting to build any device that manipulates spacetime on such scales. Despite these challenges, the recent proposals for faster-than-light travel represent a genuine scientific conversation about possibilities that were once relegated to the realm of fantasy. This conversation is happening in academic journals, at conferences, in research institutions. It involves serious physicists with credentials and expertise, not fringe figures promoting pseudoscience. The papers being published are subjected to peer review, scrutinized by other experts, critiqued and refined through the normal processes of science. This does not mean that the conclusions are correct or that warp drives will ever be built, but it does mean that the question is being taken seriously, treated as a legitimate area of inquiry rather than dismissed out of hand. Why has this shift occurred? Part of the reason is progress in our understanding of general relativity and quantum field theory. As our mathematical and computational tools have improved, we have been able to analyze more complex solutions to the Einstein field equations, to explore the parameter space of possible spacetime geometries, to identify configurations that might have been overlooked or dismissed in earlier decades. Part of the reason is the growing realization that the universe is far stranger than we once imagined. Discoveries in cosmology, such as the acceleration of the universe's expansion driven by dark energy, suggest that there are aspects of spacetime and gravity that we do not fully understand. If dark energy can cause the universe to expand at an accelerating rate, if it represents a kind of negative pressure or exotic energy density, then perhaps other exotic configurations are possible. Another factor is the increasing sophistication of our observational tools. Instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, have detected gravitational waves ripples in spacetime itself caused by the collision of black holes and neutron stars. These observations confirm that spacetime is not a static backdrop, but a dynamical entity that can wave, bend, and vibrate. Each new observation, each new data point, refines our understanding of how spacetime behaves under extreme conditions, and this understanding feeds back into theoretical work on exotic propulsion mechanisms. There is also a cultural factor at play. The exploration of space has always been driven by a combination of scientific curiosity, practical necessity, and the human desire to transcend boundaries, to go beyond the known, to reach for the stars. But the stars are far away, so far that even the nearest ones are beyond the reach of conventional propulsion technologies. A spacecraft traveling at a significant fraction of the speed of light, say 10%, would take 40 years to reach Proxima Centauri. Building such a spacecraft would require overcoming enormous technical challenges related to energy, shielding, navigation, and life support. Even if we could build it, the astronauts who embarked on such a journey would be isolated from Earth, unable to communicate in real time, aging and perhaps dying before their destination was reached. For interstellar travel to become practical, for humanity to become a truly spacefaring species spreading beyond our solar system, we need something better than conventional propulsion. We need a way to cross light years in human lifetimes. This need, this aspiration, motivates the search for exotic propulsion mechanisms, including warp drives. It is worth reflecting on the history of human achievement in overcoming seemingly insurmountable obstacles. There was a time when human flight was considered impossible, when heavier-than-air machines were thought to violate the laws of nature. The Wright brothers proved otherwise in 1903, and within decades, aviation had transformed warfare, commerce, and society. There was a time when splitting the atom was considered a laboratory curiosity, with no practical application, yet within a generation nuclear energy was powering cities and submarines. There was a time when the idea of sending humans to the moon was dismissed as fantasy, yet in 1969, Neil Armstrong set foot on lunar soil. Each of these achievements required not just technological innovation but a willingness to challenge prevailing assumptions, to explore ideas that seemed absurd or impossible to the majority of people. The proposal that we might one day travel faster than light is, in many ways, more radical than any of these earlier achievements because it challenges something more fundamental than engineering limitations. It challenges our understanding of the structure of spacetime itself. But if history teaches us anything, it is that our understanding of nature is always provisional, always subject to refinement and revision. The physics of Newton was thought to be complete and final until the anomalies in the orbit of Mercury and the results of the Michelson-Morley experiment revealed that something was missing. Einstein's theories of relativity resolved those anomalies but introduced new mysteries. Quantum mechanics revealed a subatomic world that defies classical intuition. Each revolution in physics has expanded the boundaries of the possible, revealing that nature is richer and stranger than we previously imagined. Could we be on the verge of another such revolution? Some physicists believe that the unification of general relativity and quantum mechanics, the long-sought theory of quantum gravity, will reveal new principles that either confirm the impossibility of faster-than-light travel or, conversely, show how it might be achieved. String theory, loop quantum gravity, and other approaches to quantum gravity all suggest that spacetime itself has a more complex structure at the smallest scales, perhaps composed of tiny loops or vibrating strings or higher-dimensional branes. If spacetime is not a smooth continuum but rather has a discrete or granular structure at the Planck scale, roughly 10 to the negative 35 meters, then the behavior of spacetime under extreme conditions might differ from what general relativity predicts. These differences might close the door on warp drives, or they might open new avenues that we have not yet considered. The Planck scale represents a kind of frontier beyond which our current theories cannot reliably predict. At this scale, the energy densities are so high, the distances so small, that both quantum mechanics and general relativity become important, and their predictions conflict. Resolving this conflict is one of the great unsolved problems in physics. Until we have a theory of quantum gravity, we cannot be certain about the behavior of spacetime under the extreme conditions that would be required for a warp drive. This uncertainty cuts both ways. It means we cannot definitively say that warp drives are possible, but it also means we cannot definitively say they are impossible. Let us consider more carefully the nature of spacetime itself, for it is the manipulation of spacetime that lies at the heart of all faster-than-light proposals. In everyday experience, space and time seem like separate things. Space is where things happen, a three-dimensional stage on which events unfold. Time is the progression of moments, the ordering of events from past to future. But relativity tells us that space and time are not separate. They are woven together into a four-dimensional continuum. Space-time and the separation of this continuum into space and time depends on the observer's state of motion. Events that are simultaneous for one observer may not be simultaneous for another observer moving at a different velocity. Distances in space and durations in time are not absolute but depend on the relative motion of the observer. This insight, revolutionary when Einstein first proposed it, has become the foundation of modern physics. Every confirmed observation, every successful experiment, every technological application from GPS satellites to particle accelerators reinforces the reality of spacetime as a unified entity. But what is spacetime made of? Is it a substance, a field, a mathematical abstraction? Physicists often speak of spacetime as if it were a physical fabric. something that can be stretched, compressed, twisted, torn. This language is metaphorical, but it reflects the fact that space-time has properties. It can be curved by the presence of mass and energy. It can carry waves, gravitational waves, that propagate at the speed of light. It can expand as the universe is expanding, carrying distant galaxies away from us. If space-time is a dynamical field with properties that can be altered by energy and momentum, then the question of whether we can manipulate it becomes a question about energy and control rather than a question about fundamental prohibitions. This is the conceptual shift that underlies the new proposals for faster-than-light travel. Instead of asking whether we can break the speed limit, we ask whether we can rearrange space-time in such a way that the speed limit becomes irrelevant. Instead of accelerating through space, we reshape space itself. To make this more concrete, consider an analogy. Imagine you are an ant walking on the surface of a rubber sheet. The rubber sheet represents two-dimensional space, and you, the ant, can walk across it at a certain maximum speed. Now suppose someone takes hold of the rubber sheet and pulls two distant points together, creating a bridge or fold in the sheet. If you walk across this bridge, you can travel between those 2 points much faster than if you had walked across the original flat sheet, even though your walking speed never exceeds your maximum speed relative to the surface of the sheet. The rubber sheet analogy is crude and omits the crucial fourth dimension of time, but it captures the essence of the idea. By altering the geometry of space, we can reduce the effective distance between 2 points, allowing travel between them in less time than light would take through unaltered space. The mathematics of general relativity provides the language for describing such geometries with precision. The metric tensor, a mathematical object that encodes the distances and angles in space-time, can take an infinite variety of forms, each describing a different possible geometry. The Einstein field equations constrain which geometries are physically realizable, relating the metric to the distribution of energy and momentum. Finding a solution to these equations that describes a warp bubble amounts to finding a specific form of the metric tensor and a corresponding energy distribution that satisfies the field equations. This is a difficult mathematical problem, but it is well defined, and progress can be made through systematic exploration of the solution space. The Alcubierre metric, the original warp drive solution, is one such form. It describes a space-time in which a region of flat space, the interior of the bubble, is surrounded by a shell where space is strongly curved. The curvature is arranged so that geodesics, the paths that free-falling objects follow through space-time, converge ahead of the bubble and diverge behind it. This convergence and divergence effectively move the bubble through space at superluminal speeds relative to distant observers. The energy distribution required to maintain this metric includes regions of negative energy density, which is why the solution is considered exotic and difficult to realize. The lens soliton, proposed more recently, takes a different approach. Instead of a static bubble maintained by a continuous input of exotic energy, the lens solution describes a wave-like disturbance that propagates through spacetime. This soliton, a self-reinforcing wave, maintains its shape as it travels, and it can carry a spacecraft along with it. The key innovation in Lenz's work is the claim that such solitons can be constructed using only positive energy, specifically by arranging matter and energy in carefully designed configurations that produce the necessary spacetime curvature. The energy densities required are enormous, but they do not involve the theoretically problematic negative energy that plagued earlier models. Other researchers have explored variations on these themes, investigating different shapes for the warp bubble, different distributions of energy, different mathematical techniques for solving the field equations. Some have considered hyperfast solitons that travel faster than light but do not require negative energy. Others have examined the possibility of using rotating masses or electromagnetic fields to generate the necessary curvature. Still others have looked at quantum corrections to the classical field equations, asking whether quantum effects might enhance or suppress the feasibility of warp drives. The diversity of approaches reflects the fact that we are still in the early stages of understanding what is possible. We are exploring a vast landscape of potential solutions, most of which will turn out to be dead ends. but some of which may point the way toward achievable technologies. One particularly intriguing line of research involves the concept of wormholes, hypothetical tunnels through spacetime that connect distant regions. Wormholes, like warp drives, are solutions to the Einstein field equations, and they too require exotic matter or negative energy to remain stable and traversable. A traversable wormhole would allow instantaneous travel, or at least faster than light travel, between 2 points in space, effectively serving as a shortcut through the fabric of space-time. The connection between wormholes and warp drives is more than superficial. Both involve manipulating space-time to reduce the effective distance or time required for travel. Some physicists have speculated that a warp drive might actually create a kind of temporary wormhole, a brief tunnel that exists only as long as the drive is operating. If so, understanding wormholes might provide insights into the feasibility and engineering of warp drives. Wormholes also raise questions about causality and time travel. If a wormhole connects 2 points in space, and if one mouth of the wormhole is moved relative to the other at relativistic speeds, the time experienced by an observer entering one mouth and exiting the other may differ from the time experienced by an observer remaining outside. Under certain conditions, this could allow travel into the past, creating closed time-like curves and all the associated paradoxes. Whether such configurations are actually possible, or whether some deeper principle of physics prevents them, remains an open question. Some physicists invoke the chronology protection conjecture, proposed by Stephen Hawking, which suggests that the laws of physics conspire to prevent the formation of closed time-like curves, thus preserving causality. But this conjecture is not proven, and it remains possible that the universe does permit time travel under certain extreme conditions. The exploration of these ideas, warp drives, wormholes, time travel, may seem like abstract mathematical games, far removed from the practical concerns of engineering and technology. But it is precisely through such abstract exploration that the boundaries of the possible are mapped. Before we can build something, we must first understand whether it can exist. Before we can engineer space-time, we must understand the rules that govern it. The theoretical work being done today, the papers being published, the solutions being explored, lay the groundwork for technologies that may emerge in the distant future. It is also worth noting that even if faster-than-light travel proves impossible, the pursuit of this goal will likely yield valuable insights and spin-off technologies. The study of exotic spacetime geometries deepens our understanding of general relativity and quantum field theory. The exploration of energy sources like antimatter and vacuum energy could lead to new propulsion systems, even if they fall short of enabling warp drives. The development of computational techniques for solving the Einstein field equations has applications in astrophysics, cosmology, and gravitational wave astronomy. The history of science is full of examples where the pursuit of one goal led to unexpected discoveries in entirely different areas. The quest to transmute lead into gold, though ultimately futile, gave rise to modern chemistry. The search for a perpetual motion machine, though impossible, led to the formulation of the laws of thermodynamics. The pursuit of faster-than-light travel, even if it never succeeds, may yet transform our understanding of the universe. There is another dimension to this discussion that should not be overlooked, the philosophical and existential dimension. The speed of light is not just a physical constant. It is a symbol of limitation, a reminder that we are finite beings in an almost infinite universe. The vast distances between stars are not merely inconvenient. They are isolating. They mean that we are, for practical purposes, confined to our tiny corner of the galaxy. The light from distant galaxies carries information about events that happened millions or billions of years ago, events we can observe but never influence or reach. We are spectators to the universe, not participants across its full extent. This isolation is humbling, but it is also for some intolerable. The desire to overcome it, to find a way to reach the stars within human lifetimes, is not just a practical concern but a deep psychological and cultural impulse. Humans are explorers by nature. We have spread across the surface of the earth, climbed its highest mountains, dove to its deepest oceans, ventured into space and set foot on the moon. Each frontier, once crossed, has expanded our sense of possibility, our understanding of our place in the cosmos. But the interstellar frontier is of a different order. It is not merely distant, but, with current technology, effectively unreachable. The nearest potentially habitable exoplanet is many light-years away, a distance that conventional propulsion cannot bridge within a human lifetime. If we are to become an interstellar species, if we are to fulfill the vision articulated by scientists and science fiction writers alike, we need a breakthrough. We need faster-than-light travel, or something equivalent to it. This is where the recent proposals become more than academic exercises. They represent a glimmer of hope, a suggestion that the universe might not be as closed off to us as we once thought. They suggest that the barriers we face are technological and energetic rather than absolute and fundamental. This shift in perspective, from impossible to extraordinarily difficult, changes the nature of the challenge. It transforms faster-than-light travel from a fantasy into a long-term engineering goal, something that might be achieved by our descendants, if not by us. But we must also be realistic about the timescales involved. Even if the theoretical obstacles to faster-than-light travel can be overcome, the practical obstacles are staggering. The energy requirements alone place such technologies centuries or millennia beyond our current capabilities. We do not yet have controlled fusion, let alone antimatter reactors or vacuum energy extractors. We do not yet have a complete theory of quantum gravity, let alone the ability to engineer space-time on macroscopic scales. We do not yet have the computational power to simulate and control the dynamics of warp bubbles in real time. These are not problems that will be solved in a decade or even a century. They are grand challenges that may occupy humanity for hundreds or thousands of years, if they can be solved at all. Yet the pursuit of such challenges has intrinsic value. It pushes the boundaries of human knowledge and capability. It inspires new generations of scientists and engineers. It fosters international collaboration and the sharing of ideas. It reminds us that we are part of a larger story, a story that began with the first humans looking up at the night sky and wondering what lies beyond. A story that continues today with probes exploring the outer solar system and telescopes peering into the depths of the cosmos. A story that might one day include journeys to other stars. Let us now return to the specifics of the recent proposals and examine them in greater detail. The Alcubierre metric, as we have discussed, describes a spacetime with a bubble moving through it. Mathematically, the metric is expressed in terms of a shape function that defines the bubble's geometry and a velocity function that describes how the bubble moves. The shape function is typically chosen to be smooth, transitioning gradually from the flat interior to the curved exterior, in order to avoid singularities or discontinuities that would be physically problematic. The velocity function determines the speed of the bubble relative to distant observers. In principle, this speed can be arbitrarily large, limited only by the amount of energy available and the stability of the configuration. The energy-momentum tensor associated with the Alcubierre metric, which describes the distribution of energy and momentum required to maintain the space-time geometry, has several notable features. First, as mentioned, it includes regions of negative energy density. These regions are located primarily in the shell surrounding the bubble, where the curvature is strongest. Second, the energy density scales with the velocity of the bubble and with the thickness of the shell. The faster the bubble moves and the thinner the shell, the greater the energy density required. This is why modifications that increase the shell thickness can reduce the total energy requirements, though at the cost of a less compact bubble. Third, the energy-momentum tensor may violate not only the weak energy condition, but also the null energy conditions and other energy conditions that physicists use to ensure physical plausibility. These violations are the crux of the debate over the feasibility of warp drives. If the energy conditions are truly fundamental, reflecting deep principles of quantum field theory or thermodynamics, then the Alcubierre metric, despite being a valid mathematical solution, may not correspond to any physically realizable state. Some physicists argue that quantum effects will prevent the formation of macroscopic regions of negative energy density, Much like quantum fluctuations allow temporary violations but suppress sustained ones. Others argue that the energy conditions are merely useful guidelines, not inviolable laws, and that sufficiently advanced technology might find ways to circumvent them, perhaps by exploiting loopholes in quantum field theory or by using configurations that approach but do not strictly violate the conditions. Harold White's modifications to the Alcubierre metric were motivated by the desire to reduce the energy requirements to levels that, while still enormous, are at least conceivable for a far future civilization. By changing the shape of the bubble from a simple sphere to a more toroidal form, White and his colleagues found that the energy requirements dropped by several orders of magnitude. This reduction occurs because the toroidal geometry allows the energy to be distributed more efficiently, reducing the peak energy density in any given region. The modified metric still requires negative energy, but the total amount is much smaller, potentially within the range of what advanced antimatter or vacuum energy technologies might provide. White's work also explored the possibility of detecting spacetime distortions associated with warp bubbles. If a warp bubble could be created, even a tiny one, it would produce measurable effects on nearby light beams, causing them to refract or interfere in characteristic ways. White and his team at NASA conducted experiments using a device called a White-Judet warp field interferometer, which uses laser interferometer to search for tiny distortions in spacetime. The experiments were preliminary and the results inconclusive, but they represented a serious attempt to move the study of warp drives from pure theory into the realm of experimental physics. The fact that such experiments are being conducted at a major research institution like NASA signals a shift in how the scientific community views these ideas. Eric Lentz's proposal, published in 2021, took a different tack. Lentz sought to construct warp drive solutions that avoid negative energy entirely, using only conventional positive energy. His approach was to look for soliton solutions to the Einstein field equations, stable wave packets that propagate through spacetime without dispersing. Solitons are well known in other areas of physics, appearing in nonlinear optics, fluid dynamics, and condensed matter systems. Lentz applied similar mathematical techniques to general relativity, searching for soliton-like configurations of spacetime curvature. What Lentz found was that certain classes of solitons, which he called hyperfast solitons, could travel faster than light while satisfying the null energy condition, a weaker constraint than the weak energy condition, but still physically significant. These solitons require enormous energy densities, comparable to the mass energy of entire planets compressed into small volumes, but they do not require negative energy. This is a significant conceptual advance because it eliminates one of the main theoretical objections to warp drives. If Lentz's solutions are correct and physically realizable, then faster-than-light travel becomes a matter of engineering rather than a matter of fundamental physics. However, Lentz's work has not been without criticism. Some physicists have questioned whether the solitons he describes are truly stable, whether they could be generated by any realistic process, and whether they would maintain their shape over long distances. The energy densities required, while positive, are still far beyond anything we can currently achieve or even imagine achieving in the foreseeable future. Nevertheless, the work has sparked renewed interest in warp drives and has led to further research exploring variations on Lentz's approach. Another recent development involves the application of quantum field theory to the problem of exotic matter. In classical general relativity, negative energy densities are simply assumed as part of the energy momentum tensor without worrying about where they come from or how they are maintained. But in quantum field theory, the vacuum is not empty, and its energy properties are determined by the quantum fields that permeate space. The Casimir effect, as discussed earlier, is one manifestation of these properties. Some researchers have investigated whether the quantum vacuum could be manipulated to produce the negative energy densities required for warp drives. The idea is subtle. The vacuum has an average energy density, often taken to be zero by convention, but local variations around this average can be positive or negative. The Casimir effect produces a region between two plates where the energy density is lower than the surrounding vacuum, effectively negative relative to the average. If this principle could be scaled up, if we could create and stabilize large regions of reduced vacuum energy, then we might have a source of the exotic matter needed for warp drives. The challenge is that the Casimir effect is extraordinarily weak, producing measurable forces only at nanometer scales. Scaling it up to macroscopic sizes would require revolutionary advances in nanotechnology, materials science, and our understanding of quantum fields. There are also approaches based on modifying the Einstein field equations themselves. Some theories of modified gravity propose to explain dark matter or dark energy without invoking new particles or exotic energy forms, alter the relationship between spacetime curvature and energy momentum. In some of these theories, solutions analogous to warp drives might exist without requiring exotic matter. However, these theories are speculative and not as well tested as general relativity. They introduce additional parameters or fields that must be constrained by observations, and so far, no modified gravity theory has gained widespread acceptance as a replacement for general relativity. Nevertheless, the exploration of such theories is valuable because it probes the boundaries of our understanding of gravity and spacetime. We should also consider the possibility that our current understanding of physics is incomplete in ways that we do not yet recognize. The history of science is a history of revolutions, of paradigm shifts that completely change how we view the world. Classical mechanics was overturned by relativity and quantum mechanics. The understanding of the atom evolved from indivisible particles to complex structures of quarks and leptons. The universe itself, once thought to be static and eternal, is now known to be expanding and evolving, originating in a Big Bang some 13.8 billion years ago. Each of these revolutions revealed new phenomena and new principles that were previously unimagined. Could we be on the brink of another such revolution? Some physicists believe that the synthesis of quantum mechanics and general relativity will lead to entirely new concepts, new dimensions, new forces, new particles. String theory, for instance, posits that the fundamental constituents of reality are not point-like particles but tiny vibrating strings, and that the universe has not 4 dimensions but 10 or 11, with the extra dimensions curled up too small to observe directly. Loop quantum gravity suggests that spacetime itself is quantized, made up of discrete units at the Planck scale, much like matter is made up of atoms. These theories are far from complete and have not yet made predictions that can be definitively tested, but they represent serious attempts to go beyond the standard model of particle physics and general relativity. If either of these theories or some other theory of quantum gravity turns out to be correct, it could have profound implications for the possibility of faster-than-light travel. New dimensions might provide shortcuts through space. New symmetries might allow violations of energy conditions that are forbidden in 4-dimensional spacetime. New quantum effects might enable the manipulation of spacetime in ways we cannot currently imagine. Conversely, a theory of quantum gravity might impose new constraints that definitively rule out warp drives and faster-than-light travel. Until we have such a theory confirmed by experiment, we cannot be certain. The experimental search for quantum gravity is one of the great endeavors of modern physics. Particle accelerators like the Large Hadron Collider probe the behavior of matter and energy at the highest energies accessible to human technology, searching for deviations from the standard model that might hint at new physics. Gravitational wave observatories like LIGO and Virgo observe the universe in a completely new way, detecting the ripples in spacetime produced by colliding black holes and neutron stars, events that involve extreme conditions where quantum gravity effects might be detectable. Space-based telescopes study the cosmic microwave background, the faint afterglow of the Big Bang, looking for subtle patterns that could reveal the quantum structure of the early universe. Each of these experimental programs contributes to our understanding of the fundamental laws of nature, and each has the potential to uncover clues about whether faster-than-light travel is possible. It is also worth considering the societal and ethical implications of faster-than-light travel, should it ever become possible. The ability to traverse interstellar distances in human lifetimes would transform civilization. It would enable the colonization of exoplanets, the establishment of human settlements around distant stars, the spread of human culture and biology across the galaxy. This expansion would raise profound questions about identity, governance, and the relationship between different human communities separated by light years. It would also raise questions about our responsibilities to other forms of life. If we encounter alien civilizations, or if we discover biospheres on other planets, how should we interact with them? The prime directive of Star Trek, the principle of non-interference in the development of less advanced civilizations, is a fictional concept, but it reflects real ethical concerns about the impact of contact between societies at different levels of technological development. There are also risks. A civilization capable of manipulating space-time and energy on the scales required for warp drives would wield immense power that could be used for destruction as well as creation. The same technologies that enable interstellar travel could potentially be weaponized, used to create catastrophic distortions in space-time, or to release enormous energies in destructive ways. The ethical frameworks that guide human behavior on Earth, shaped by thousands of years of cultural evolution, may not be adequate for a spacefaring civilization. New principles, new institutions, new forms of cooperation will be needed to navigate the challenges and opportunities of the interstellar age. But these are concerns for the distant future. For now, the question is whether faster-than-light travel is possible in principle, and if so, what the path to achieving it might look like. The recent proposals suggest that the answer to the first question is maybe, and the answer to the second question is long, difficult, and uncertain. We are at the very beginning of a journey that may span centuries or millennia, a journey that will require not just technological innovation but fundamental advances in our understanding of physics. One of the key insights from the recent work on warp drives is the importance of energy efficiency and the geometry of space-time distortions. Small changes in the shape or structure of a warp bubble can have large effects on the energy requirements and the feasibility of the configuration. This suggests that future research should focus not just on finding solutions to the Einstein field equations, but on optimizing those solutions, searching through the vast parameter space for configurations that minimize energy requirements, maximize stability, and avoid the most severe violations of energy conditions. This is a task well suited to modern computational tools, including machine learning algorithms that can explore high-dimensional parameter spaces and identify promising regions for further investigation. Machine learning and artificial intelligence are already being used in physics to discover new materials, optimize experimental designs, and analyze complex data sets. Applying these techniques to the problem of warp drives could accelerate progress, identifying configurations that human intuition might overlook. However, computational power alone is not enough. We also need deeper theoretical understanding, clearer insights into the relationship between energy, momentum, and spacetime curvature, and better knowledge of how quantum effects modify the predictions of classical general relativity. Another promising direction is the study of analog systems, physical systems that mimic the behavior of spacetime in certain respects. For example, flowing fluids can exhibit phenomena analogous to black holes and event horizons, a subject studied in the field of analog gravity. These analog systems do not involve actual spacetime curvature, but they provide testbeds for exploring concepts and mathematical techniques that might be applicable to warp drives. If we can create and study analog warp bubbles in laboratory settings, even if they involve sound waves in fluids rather than actual space-time distortions, we might gain insights into the stability, control, and dynamics of warp configurations. There is also the question of incremental progress. Even if full-scale warp drives are beyond our reach for the foreseeable future, might we be able to achieve partial effects, small distortions of space-time that produce measurable propulsion or other useful phenomena? This is the philosophy behind some of the experimental work being done, the idea that we can begin to explore the engineering of spacetime on small scales, learning as we go, building up the knowledge base that will eventually enable larger and more ambitious projects. This incremental approach is how most technological revolutions occur, through the accumulation of small advances, each building on the last, gradually transforming the impossible into the routine. Consider the analogy to flight. The Wright brothers' first aircraft flew for just 12 seconds, covering a distance of 120 feet. By modern standards, it was barely flight at all, a brief hop rather than sustained travel. But it was proof of concept, a demonstration that heavier-than-air flight was possible. Within a few decades, aircraft were crossing oceans and continents. Within a century, they were carrying hundreds of passengers at nearly the speed of sound. The first step, the proof that something can be done at all, is often the most difficult, and it is the most important. If we can create even a tiny warp effect, a measurable distortion of space-time in a controlled setting, it would transform the conversation about faster-than-light travel from speculation to engineering. This brings us to the role of funding and institutional support. Major technological advances require sustained investment, not just in terms of money, but in terms of intellectual effort, infrastructure, and collaboration. The development of nuclear energy, the space program, the Internet, all required government and institutional support over many years. The same will be true for any attempt to develop faster-than-light propulsion. This is not a project that can be undertaken by individuals or small groups working in isolation. It requires the resources and coordination of nations, or of international collaborations, and it requires a commitment to long-term goals that may not yield immediate practical benefits. Public interest and support are also crucial. Science and technology advance most rapidly when there is broad enthusiasm and engagement. When young people are inspired to pursue careers in physics and engineering, when societies value exploration and discovery. The recent proposals for faster-than-light travel have captured public imagination, appearing in news articles, popular science books, and online discussions. This attention is valuable because it raises awareness of the questions being explored and the challenges being faced. It also creates pressure on funding agencies and policymakers to support research in these areas, to recognize that the quest to reach the stars is not just science fiction, but a legitimate scientific endeavor. However, we must also be careful not to overpromise or to create unrealistic expectations. The path from theoretical possibility to working technology is long and uncertain, and most attempts fail. For every successful innovation, there are countless failed experiments, discarded theories, and abandoned projects. The pursuit of faster-than-light travel may ultimately prove futile, not because the physics is impossible, but because the engineering challenges are insurmountable, or because we discover that deeper principles of nature prevent such technologies from being built. It is important to communicate both the excitement and the uncertainty, to celebrate the progress being made while acknowledging the enormous obstacles that remain. In the context of this discussion, it is also important to consider alternative approaches to interstellar travel that do not require faster-than-light propulsion. Generation ships, massive spacecraft that travel at sublight speeds with populations of humans living and dying aboard over many generations, are one such approach. Another is suspended animation or cryogenic preservation, technologies that would allow astronauts to sleep through the long journey and awaken at the destination. Yet another is the concept of uploading human consciousness into digital form, allowing minds to be transmitted at the speed of light to robotic bodies waiting at distant stars. Each of these approaches has its own challenges and ethical considerations, and none is anywhere near practical realization, but they represent alternative pathways to becoming an interstellar civilization. That said, faster-than-light travel, if achievable, would be vastly superior to any of these alternatives. It would allow travel within human lifetimes, preserving continuity of experience and culture. It would enable exploration and colonization on timescales relevant to individual lives, rather than requiring multi-generational commitments. It would make the stars accessible in a way that sublight travel never could. This is why the dream persists, and why scientists continue to explore the boundaries of the possible. Let us delve deeper into the mathematical structure of spacetime and how it relates to the possibility of faster-than-light travel. Spacetime in general relativity is described by a metric, a mathematical object that tells us how to measure distances and times. The metric can be thought of as a field that varies from point to point, and the curvature of this field is determined by the distribution of matter and energy, according to the Einstein field equations. These equations are nonlinear, meaning that the curvature at one point depends on the curvature at other points in a complicated way. This nonlinearity makes the equations difficult to solve, but it also allows for a rich variety of solutions, including black holes, gravitational waves, expanding universes, and, potentially, warp drives. A key feature of the Einstein field equations is that they are local, meaning that the curvature at a given point depends only on the energy and momentum at that point and its immediate neighborhood. This locality is related to the fact that gravity, like all forces in relativity, propagates at the speed of light. Changes in the gravitational field do not instantaneously affect distant regions. They propagate outward as gravitational waves. This locality is both a constraint and an opportunity. It is a constraint because it means we cannot simply declare that space should be contracted in one region and expanded in another. We must provide a physical mechanism, a distribution of energy and momentum, that produces the desired curvature, but it is also an opportunity because it means that the effects of a warp drive are confined to a limited region, the bubble and its immediate surroundings, and do not require coordinating changes across the entire universe. The challenge is to find energy distributions that produce the desired curvature while remaining physically plausible. This is where the energy conditions come into play. The weak energy condition, for example, requires that the energy density measured by any observer be non-negative. This condition is motivated by the idea that energy should not be able to flow backward in time, and it rules out certain pathological solutions like negative mass particles that would accelerate when pushed backward. But the weak energy condition is not a fundamental law. It is a heuristic principle, and there are situations in quantum field theory where it can be violated temporarily on small scales. The question is whether these temporary microscopic violations can be harnessed and amplified to produce the macroscopic negative energy densities required for a warp drive. Some physicists are optimistic, pointing to the Casimir effect and other quantum phenomena as proof that negative energy is real and can be manipulated. Others are skeptical, arguing that the second law of thermodynamics and other principles will prevent any significant accumulation or amplification of negative energy. The debate is ongoing, and it will likely not be resolved until we have a complete theory of quantum gravity that can definitively answer questions about the behavior of energy and spacetime at all scales. Another important aspect of the mathematics is the question of singularities. A singularity is a point or region where some physical quantity becomes infinite, indicating a breakdown of the theory. Black holes have singularities at their centers, where the curvature of spacetime becomes infinite according to classical general relativity. Warp drive solutions might also contain singularities, particularly if the energy density or spacetime curvature becomes extremely large in the bubble wall. Singularities are problematic because they represent regions where our equations cease to make sense, where we cannot predict what will happen. Quantum gravity is expected to resolve singularities, replacing them with smooth, finite structures. But until we have such a theory, singularities remain a warning sign that a solution may not be physically realizable. Stability is another critical mathematical question. Even if a solution to the Einstein field equations exists and satisfies all energy conditions, it may be unstable, meaning that small perturbations cause it to collapse or grow uncontrollably. Stability analysis involves perturbing the solution slightly and examining whether the perturbations grow or decay over time. For warp drives, this analysis is complicated by the fact that the bubble is moving, so the perturbations must be analyzed in a frame that moves with the bubble. Some studies suggest that warp bubbles may be unstable to certain modes of perturbation, particularly those involving the accumulation of energy at the bubble wall. If so, then maintaining a warp bubble might require continuous active control, constantly adjusting the energy distribution to counteract instabilities. This would add another layer of complexity to the engineering challenge. There is also the question of how a warp bubble would interact with the matter and radiation it encounters as it travels through space. Interstellar space is not empty. It contains gas, dust, cosmic rays, and photons from various sources. As a warp bubble moves through this medium, it might sweep up particles and radiation, concentrating them at the bubble wall or within the bubble. The accumulated energy could affect the stability of the bubble, or it could be released catastrophically when the bubble collapses. Some models suggest that the interaction with interstellar matter could limit the maximum speed of a warp drive, as the drag or accumulation effects become prohibitive at very high velocities. Other models suggest that the bubble might be designed to deflect or tunnel through matter without significant interaction, though the details of how this would work are unclear. The interaction with light is particularly interesting. Photons entering a warp bubble would experience extreme redshift or blue shift, depending on whether they enter from the front or the back of the bubble. This could render communication with the outside universe difficult or impossible while the bubble is in motion. It could also create intense bursts of gamma rays when the bubble collapses, as the accumulated blue-shifted photons are suddenly released. These gamma ray bursts could pose a hazard to the spacecraft, to any nearby objects, and potentially to the destination system if the bubble arrives near a planet. Understanding and mitigating these effects would be crucial for the safe operation of a warp drive. Now let us turn to the question of how a warp drive might be initiated and controlled. In most theoretical models, the warp bubble is assumed to be created around a spacecraft that is initially at rest or moving at conventional velocities. The creation of the bubble would require a sudden, dramatic rearrangement of spacetime, a process that is not well understood. It might involve the rapid deployment of exotic matter, the activation of powerful field generators, or some other mechanism that we have not yet conceived. Once the bubble is formed and moving, the challenge shifts to maintaining it and steering it. As mentioned earlier, the occupants of the spacecraft cannot easily communicate with the bubble's edge because signals travel at the speed of light, which is slower than the bubble itself. This causal disconnection is a fundamental problem. One proposed solution is to pre-program the trajectory before entering the bubble, so that the bubble automatically follows a predetermined path without requiring real-time control. Another proposal involves using external navigation beacons or relay stations that communicate with the bubble, though this requires a network of stations spread across interstellar space, a formidable infrastructure challenge. A third idea is to modulate the bubble from within by varying the energy distribution in ways that affect the bubble's motion, essentially using the internal dynamics of the spacecraft to influence the external geometry of the bubble. None of these solutions is satisfactory, and all require further theoretical and practical development. Stopping the bubble collapsing it safely at the destination is another challenge. A sudden collapse could release the accumulated energy in a burst, or it could create shock waves in spacetime that propagate outward. The process must be controlled carefully to avoid damage to the spacecraft and its surroundings. One possibility is to gradually reduce the energy driving the bubble, allowing it to slow and dissipate over time. Another is to transition from a warp bubble to a more conventional propulsion mode as the destination is approached, so that the final stages of the journey are conducted at sublight speeds using well-understood technologies. These practical challenges, while formidable, are not necessarily insurmountable. They are the kinds of problems that engineers excel at solving given sufficient time, resources, and understanding of the underlying physics. The history of technology is full of examples where theoretical principles were understood long before practical implementations were achieved. Radio waves were predicted by Maxwell's equations in the 1860s but not demonstrated until the 1880s, and not widely used until the early 20th century. Nuclear energy was understood theoretically in the 1930s but not harnessed until the 1940s. Quantum computing, based on principles discovered in the early 20th century, is only now, in the early 21st century, beginning to become practical. The gap between theory and application can be decades or even centuries, but it can be bridged if the theory is sound and the effort is sustained. In the case of warp drives, we are still in the very early stages, closer to Maxwell's equations than to practical radio. We have theoretical models, mathematical solutions, and ongoing debates about whether those solutions correspond to anything physically realizable. We do not yet have experimental demonstrations, even on the smallest scales. We do not yet have a clear technological roadmap, a sequence of steps that leads from where we are now to a working warp drive. But we have something valuable, a direction for research, a set of questions to explore, and a growing community of scientists willing to take those questions seriously. It is also important to place this work in the broader context of humanity's long-term future. We are a young species, having existed for only a few 100,000 years, and our civilization in its modern form is only a few thousand years old. We have been spacefaring for less than a century. On cosmic timescales, we are infants. But we are infants with enormous potential. The universe is vast, containing billions of galaxies, each with billions of stars, many with planets, some of which may harbor life. If humanity survives and thrives, if we avoid self-destruction and overcome the challenges of sustainability and coexistence, we could spread throughout the galaxy and beyond, becoming a spacefaring civilization that endures for millions or billions of years. But this future is not inevitable. It requires vision, effort, and the willingness to invest in long-term goals. It requires that we value knowledge and exploration, that we support science and education, that we work together across national and cultural boundaries. The pursuit of faster-than-light travel, even if it ultimately fails, contributes to this larger project. It inspires, it educates, it pushes the boundaries of what we think is possible. And if it succeeds, if we do find a way to travel faster than light, it will open the galaxy to exploration and settlement, transforming the future of humanity in ways we can scarcely imagine. There is a deep philosophical question lurking beneath all of this technical discussion. Why does the universe have the structure it does? Why is the speed of light finite? Why is spacetime four-dimensional? Why do the laws of physics take the particular mathematical form that they do? These are questions that physics, in its current form, cannot answer. Physics describes how the universe behaves, but it does not explain why the universe is structured one way rather than another. Some physicists hope that a final theory, a theory of everything, will answer these questions, showing that the laws of physics are the only logically consistent set of laws, that the universe could not have been otherwise. Others believe that our universe is just one of many in a vast multiverse, and that the laws we observe are simply the laws that happen to apply in our particular region, with different regions having different laws. If the multiverse hypothesis is correct, then it is possible that faster-than-light travel is allowed in some universes but not in others, depending on the local laws of physics. In such a framework, the question of whether we can build a warp drive becomes a question about which universe we happen to inhabit. But this is speculative in the extreme, far beyond what any current experiment can test. For now, we can only work with the laws of physics as we understand them in our universe, exploring the consequences of those laws and seeking the boundaries of what they permit. The recent proposals for faster-than-light travel, the refinements to warp drive models, the exploration of solitons and exotic matter, all represent serious scientific inquiry into these boundaries. They are not the work of cranks or charlatans, but of trained physicists working at reputable institutions, publishing in peer-reviewed journals, subjecting their ideas to scrutiny and criticism. This does not guarantee that they are correct, but it does mean that the ideas deserve consideration and further investigation. The scientific method is a process of proposing hypotheses, testing them, refining them, and discarding those that fail to match observation. This process is ongoing with regard to faster-than-light travel, and it may take many more years or decades before we have definitive answers. In the meantime, we continue to explore the universe with the tools we have. Robotic probes have visited every planet in our solar system, and some have ventured into interstellar space, carrying messages from humanity into the void. Telescopes peer deeper into the cosmos, discovering thousands of exoplanets, some in the habitable zones of their stars where liquid water could exist. Radio telescopes listen for signals from alien civilizations, searching for evidence that we are not alone. Each discovery, each new observation, adds to our understanding of the universe and informs the question of what is possible. One of the most profound discoveries of recent decades is the sheer diversity of planetary systems. Some exoplanets orbit their stars in days, scorched by intense radiation. Others are frozen worlds far from their suns. Some are rocky like Earth, while others are gas giants like Jupiter. Some orbit binary or triple star systems, experiencing complex dynamics that would make life as we know it unlikely. This diversity suggests that the universe is filled with potential destinations, places where human beings or their descendants might one day live. But reaching these destinations with conventional propulsion is prohibitively difficult. Even the closest stars require journeys of decades or centuries at relativistic speeds, speeds that are themselves extraordinarily challenging to achieve. Faster-than-light travel, if it is possible, would make these journeys feasible, opening up the galaxy to exploration and settlement. The search for extraterrestrial intelligence, SETI, is also relevant to this discussion. If intelligent life exists elsewhere in the galaxy, and if some civilizations are far more advanced than ours, they might have already solved the problem of interstellar travel. They might possess technologies that we can barely imagine, including faster-than-light propulsion. The fact that we have not detected obvious signs of such civilizations, no megastructures, no ubiquitous radio signals, no visits to Earth by alien spacecraft, is sometimes taken as evidence that interstellar travel is fundamentally impossible, or at least so difficult that even advanced civilizations do not attempt it. This is the essence of the Fermi paradox. If the galaxy is old and large, and if life arises readily, why do we not see evidence of alien civilizations everywhere? There are many possible answers to the Fermi paradox. Perhaps life is rare, arising only under very specific conditions. Perhaps intelligence is rare, even if life is common. Perhaps civilizations tend to destroy themselves before they achieve interstellar travel, a sobering thought given humanity's current challenges. Or perhaps interstellar travel is indeed extremely difficult, and even advanced civilizations remain confined to their home systems or immediate neighborhoods. The absence of evidence for alien visitors does not definitively prove that faster-than-light travel is impossible, but it does suggest caution in our expectations. If such travel were easy, we might expect a galaxy to be teeming with evidence of it. The silence might indicate that it is not easy, or that it is not possible, or that we are looking in the wrong places or in the wrong ways. Yet the universe continues to surprise us. Dark energy, the mysterious force driving the accelerated expansion of the universe, was not predicted by theory, but was discovered through observations of distant supernovae in the late 1990s. Dark matter, which makes up most of the mass of the universe, was inferred from the motion of galaxies and the bending of light around galaxy clusters, but its nature remains unknown. These discoveries remind us that our understanding of the universe is incomplete, that there are phenomena we have not yet explained, and that future discoveries may overturn or dramatically revise our current theories. It is conceivable, though far from certain, that some future discovery will reveal new principles or new phenomena that make faster-than-light travel easier or more natural than we currently believe. This brings us to the role of imagination in science. Science is often portrayed as a purely rational enterprise, a matter of logic and evidence, and to a large extent this is true. But science also requires imagination, the ability to conceive of possibilities that have not yet been observed, to ask what-if questions, to explore hypothetical scenarios and see where they lead. The great advances in physics have often come from imaginative leaps, from Einstein imagining riding on a beam of light, from Heisenberg imagining the uncertainty inherent in quantum measurements, from Dirac imagining antiparticles before they were discovered. The proposal that we might travel faster than light by warping spacetime is an imaginative leap, grounded in the mathematics of general relativity, but extending beyond what has been observed or confirmed. This imaginative dimension is part of what makes science exciting and what draws people to it. The prospect of exploring the stars, of discovering alien worlds, of encountering other forms of life, of pushing the boundaries of the possible resonates deeply with the human spirit. It connects to ancient myths and stories about heroes journeying to distant lands, about explorers crossing uncharted seas, about pioneers settling new frontiers. The technologies change, the scales change, but the underlying drive to explore and discover remains constant. As we approach the conclusion of this exploration, it is worth reflecting on what we have learned and what remains unknown. We have learned that the speed of light is not just a speed but a fundamental feature of space-time, a limit on causation and information transfer that is woven into the structure of reality as we understand it. We have learned that general relativity, the theory that describes gravity as the curvature of space-time, allows for solutions where space-time itself can be manipulated in ways that might enable effective faster-than-light travel without violating local physics. We have learned that these solutions require extraordinary energy densities and, in many cases, exotic forms of matter or energy that may not exist or may be extremely difficult to generate. We have learned that the energy requirements, once thought to be absurdly large, might be reducible through clever modifications to the geometry of warp bubbles. We have learned that recent proposals such as the lens solitons suggest that it might be possible to construct warp drives using only positive energy, eliminating one of the major theoretical objections. And we have learned that the question of whether faster-than-light travel is possible remains open, subject to ongoing research and debate. What remains unknown is vast. We do not know whether the energy conditions that forbid negative energy densities are truly inviolable, or whether they can be circumvented through quantum effects or clever engineering. We do not know whether warp bubbles can be made stable and controllable, or whether they are inherently unstable and prone to catastrophic collapse. We do not know how to generate the enormous energy densities required, or how to shape those energies into the precise configurations needed to warp spacetime. We do not have a complete theory of quantum gravity that can tell us definitively what happens to spacetime at the smallest scales or under the most extreme conditions. We do not know whether there are deeper principles not yet discovered that prohibit faster-than-light travel even if the known laws of physics allow it. And we do not know how long it might take to answer these questions, whether it is a matter of decades, centuries, or millennia. But the fact that we do not know is not a reason to stop asking. It is, in fact, the reason to continue. The pursuit of knowledge, the exploration of the unknown, is one of the defining features of human civilization. We are a species that asks questions, that seeks to understand, that refuses to accept that anything is forever beyond our reach. The proposal that we might one day travel faster than light is, at its core, an expression of this refusal, a declaration that the barriers we face are not absolute, that the universe is more wondrous and more malleable than we yet realize, and that with sufficient effort and ingenuity, we might yet find a way to cross the vast distances that separate us from the stars. The journey to the stars, whether it takes decades or millennia, whether it involves warp drives or some other technology yet to be imagined, will be one of the greatest adventures in the history of our species. It will test our courage, our creativity, our ability to cooperate and to endure. It will transform us, as all great journeys do, forcing us to confront the limits of our knowledge and the vastness of the cosmos. And it will connect us to something larger than ourselves, to the grand sweep of cosmic evolution, to the history of the universe from the Big Bang to the present, and to the future that stretches out before us, unknowable but full of possibility. In the quiet of the night, when we look up at the stars, we are looking across immense distances and immense times, seeing light that has traveled for years or centuries to reach our eyes. Each point of light is a sun, perhaps with planets, perhaps with life, perhaps with civilizations of their own, looking back at us across the void. The distances are staggering, but they are not infinite. The journey is difficult, but it is not impossible. And the dream, the vision of human beings walking on distant worlds, of explorers venturing out into the galaxy, of a civilization that spans the stars, is a dream worth pursuing, no matter how long it takes, no matter how uncertain the outcome. The recent proposals that scientists have put forward, suggesting new ways to travel faster than light by manipulating space-time, are small steps in a much larger journey. They are not the end, but the beginning, the first tentative explorations of a vast frontier that may take generations or longer to fully explore. They remind us that the universe is full of mysteries, that our understanding is always incomplete, and that the boundaries of the possible are not fixed, but shift as our knowledge grows. They invite us to imagine, to calculate, to experiment, to dream, and to work toward a future where the stars are not distant points of light, but destinations within reach. And so we continue, driven by curiosity and wonder, by the desire to know and to explore, by the conviction that the universe is comprehensible and that its secrets can be unlocked through patience and effort. We continue because the alternative, to accept our confinement, to abandon the dream of reaching the stars, is unthinkable. We continue because we are human, and reaching beyond our grasp is what we do. The speed of light may be a barrier, but it is not a wall. Spacetime may be rigid, but it is not immutable. The universe may be vast, but it is not forever beyond us. And in that possibility, however distant, however uncertain, lies hope and purpose and the promise of a future among the stars. The screen fades, not to black, but to the deep blue of space, sprinkled with points of light, each one a sun, each one a destination, waiting.